All right, welcome back, folks. Hope everybody's doing well. Today what we're going to do is take a look at oxidation numbers, how to assign oxidation numbers. What's the deal with oxidation and reduction? Now the slide that I have up here shows us oxidation and reduction, and it gives us a little definition. It tells us that oxidation here, it tells us that it is the loss of electrons. So loss of electrons. And then reduction on the other hand, is going to be the gain of electrons. The gain of electrons. Now back in the olden days, people didn't know what electrons were, and they found that if you react oxygen with some things, something happened, it changed, and so they called that oxidation. That was the old definition, it was just reacting it with oxygen. And so in this example here, we have iron, and iron reacts with oxygen. So we have Fe solid reacts with O2 gas, and this gives us Fe2O3 solid here, like this. And we balance this by throwing some stoichiometric coefficients on there, so we have the same number of atoms on both sides. Now, what's happening with the electrons? Well, over here, iron we see doesn't have a charge on it. But on the right-hand side, iron does have a charge on it. It is a cation over here, and we can look at the formula to give us a clue as to what the charge is. So as we take a look at this Fe2O3, can we make a prediction as to what the Roman numeral would be, or what would be the charge on that iron atom? +3. Yeah, excellent. It's +3. How did you know this? What witchcraft is this? How did you know it's +3? Just kind of did that crossing thing, right? So like whatever number is here has to go up here sort of thing. So this is a 3 plus, and then oxygen is a 2 minus. Excellent, yeah. And if you look at your periodic tables and you see where oxygen is on the periodic table, oxygen would pick up 2 electrons to have that Nobel gas configuration. So oxygen is typically a 2 minus. All right. Now on this side over here, they don't have charges. So we'll go like this, we'll see 0 and 0 like this. So what's happening? We can see here that the iron goes from a 0 to a 3 plus. So that means that it lost electrons. So the iron lost electrons. So we would say here that the iron has been oxidized. Iron has been oxidized. It has lost electrons. You can see that the charge here went up. Now this gets a little tricky because you're removing a negative. You're removing something with a negative charge, and so that makes this positive. Okay. All right. Now, reduction, on the other hand, here, if we go reduction is the gain of electrons. So if I take this reaction and let's see, let me try something a little different here. I'm going to go Fe2O3 solid plus 3 plus carbon monoxide gas gives me Fe solid plus CO2 gas like this. And then I'll throw in some stoichiometric coefficients to balance this, like this, and like this. Now this is a reaction that's used in steel mills to turn iron oxide, which is iron ore, into iron. And if we take a look at our charges on this, I'm just going to take the charges off of here. I have a 3 plus and a 2 minus there. And then iron here by itself doesn't have a charge. So we can see here the iron went from a 3 plus down to a 0. So that gained electrons. Electrons were gained by the iron over here. And so we would say here that the iron has been reduced. Iron has been reduced. And the way that I try to keep these apart is like, what's been oxidized? What's been reduced? How do I remember this? Is I look and I see the charge. If the charge goes down, went from a 3 plus down to a 0. If the charge goes down, it's been reduced. That's just how I remember. Now there's other ways of doing this. There's like Leo says Gur, an oil rig. Maybe you've heard of these. So like oil, O-I-L-R-I-G. Oxidation is loss, reduction is gain. Or Leo says Gur. Okay, loss of electrons is oxidation, gain of electrons is reduction. Okay, either of those work. In my brain, I just look to see if the charge goes down, it's reduced. If the charge goes down, it's been reduced. Question?
Is this still called oxidation reduction if you have your oxygen level depending on how well
Yeah, so the question is, well, do you have to have oxidation? Do you have to have oxygen to have oxidation reduction? And the answer is no, you do not. So way back in the day, before people knew what electrons were, it was only with oxygen. Either it reacted with oxygen or produced oxygen. Now we know that it's the electrons, but the name stuck. And so that's why we still call it oxidation reduction, even though there may not be any oxygen involved whatsoever. One of those old things that just kind of sticks with us. Any other questions? Okay. All right. Then let's see here. Now, we need to be able to assign oxidation numbers. And on this iron Roman numeral 3 oxide, we had some help. And you identified, okay, well, we just kind of cross-multiplied and we were able to figure this out. Now, there are actually rules for assigning oxidation numbers. And we call this a hierarchy, this hierarchy of rules. And the reason we call it a hierarchy, and that is to say the rules at the top are more important than the rules at the bottom. It's kind of like in my family. We have this hierarchy where there's certain people who have more voting power than there are other people in our family. And my children, they like to point out, well, this is a democracy and we should all have an equal voice and freedom of speech and all that stuff, which is all fine and good, except they live in the kingdom of mommy and daddy. And in the kingdom of mommy and daddy, they have veto power and absolute maniacal control. To the point that we make sure we don't have social services come to our house, but it's close. Okay. All right, so in this hierarchy, we have certain values that are more important than others. And in a textbooks, you have tables that look something like this. Now, I'm going to ask you not to copy this down directly. I'm going to write these rules on the board. I'm going to go through it kind of step by step, and I'm going to ask you to follow along and write these rules in your notes. Because the act of writing them down and going through it does help with the learning process. Helps with being able to identify what the oxidation numbers are. And many of these you're going to know already, just based on what we've covered so far. Like you were able to identify that iron has a 3+ charge and oxygen. All right, so rule number one. Rule number one for oxidation numbers. Oxidation number, I'm going to go oxidation number. Okay, oxidation number for atoms in pure elements is equal to 0. And our example of this is over here. Here's iron all by itself. And if it's iron all by itself, or an element all by itself, its charge, or its oxidation number is 0. Okay, now that's different than if we had, say, for example, Fe aqueous, like this, 3+. That's different. This is an iron ion floating in solution, it has a charge. That's different than, say, solid iron all by itself. It doesn't have a charge, and its oxidation number is 0. So elements all by themselves are 0. Examples of this might be iron solid is 0, chlorine gas is 0, and oxygen gas is 0. That's different than ions dissolved in water. That's different than aqueous solutions. Okay. Number 2, the oxidation number is equal to the charge on monoatomic ions, equal to the charge on monoatomic ions. And examples of this would be like chlorine, aqueous. So if it's chlorine dissolved in water and it is an ion, whatever that charge is, if it's a 1 minus charge, well, that's going to be equal to the oxidation number. So like sodium, aqueous, what would the charge be on that? +1. +1. And so our oxidation number would be +1 there. Okay, excellent. And just kind of like a way to remember certain ones is group 1A is always equal to +1, and group 2A is equal to +2. Okay. Now, having said that, hydrogen is going to be an exception. We're going to find out that sometimes hydrogen does some weird stuff. Okay. So there's all these rules, and then there's exceptions. Rule number 3. Rule number 3 is an easy one. Oxidation number of fluorine is equal to -1. It's always -1. If we see fluorine in something, it's going to be a -1. Okay. Any questions so far? It's pretty straightforward. This is where it's going to get a little weird now. Oxygen. Oxygen gets its own line because it does some weird things. So the oxidation number of oxygen is equal to a -2, except when it's not. So like 99% of the time, it's going to be a -2. But there are a few examples where it's not. And so if we have except, if it's combined with something that's higher up here on the list. Remember, this is a hierarchy, so whatever is higher up on the list takes precedent. And so if our oxygen is combined with, say, let's see, fluorine. So here's a compound that actually exists. It's OF2, oxygen difluoride. And if fluorine is a -1, then that means oxygen has to be a +2. That's a little weird, kind of an exception. In hydrogen peroxide, H2O2, like this. Hydrogen is a group 1A element, so it's typically +1. That means, to balance this out, oxygen here has to be a -1. And another compound, another example here, potassium oxide here. Potassium is a group 1 element, so oxygen has to be, I'm going to do the math on this one, it has to be a -1/2. Yeah. minus 1/2. And you're like, what? Fractions? Oh, that is like so algebra ninth grade, right? But yeah, actually we have oxidation numbers that could be fractions. Okay. All right. Now oxygen 99% of the time is a -2. The only reason it would not be a -2 is if it's combined with something higher up here in our hierarchy. All right. Any questions on that? Okay. Then hydrogen. Hydrogen also gets its own line. The oxidation number of hydrogen is equal to +1, except when it's not. So 99% of the time it's going to be +1. Hydrogen gives up an electron, so it can be like, a +1, except if it's combined with something higher up on the list. So for example, lithium hydroxide, like this. Lithium is a group 1A element, so that means it's a plus, and so hydrogen has to be a minus. But 99% of the time, hydrogen is going to be a +1. Okay. Then number 6, oxidation numbers. Oxidation numbers of atoms in a neutral molecule add up to 0. So oxidation numbers of neutral molecule add up to 0. So that is to say, if we have a compound such as lithium hydroxide, like this, lithium is plus, hydrogen is minus, it has to add up to 0. It has to add up to whatever the charge is on that particle. Yes, okay, so another example would be carbon dioxide. Carbon dioxide, oxygen is a -2, so carbon has to be a +4 in order to balance that out. So all of that adds up to 0. I know 4 minus 2 is not 0. -2 times 2 is -4. -4 plus 4 equals 0. Okay. And then our last rule. Our last rule, number 7, oxidation numbers of polyatomic ions add up to the charge on the polyatomic ion. Add up to the charge on the polyatomic ion. And so if we have ammonium, NH4 plus, ammonium, that's an H, okay. So hydrogen is typically a plus. So let me just go like this. I'm going to go like this just to show that all that adds up to a plus. Hydrogen is typically a plus, and there's 4 of them, so that makes nitrogen a -3, so that -3 plus 4 gives us a +1. Okay. Those are the rules. Those are the rules for assigning oxidation numbers. Now, a couple of little tidbits on this. These oxidation numbers are not the same thing necessarily as the charge. We're just saying that these are oxidation numbers. These are made up numbers that we're just making up to tell us where the electrons are going. The other thing is, if you've been paying attention, and if I've been doing my job correctly, notice that the sign goes before the number. On oxidation numbers, the sign goes before the number. So up to this point, when I've been writing like the charge on an atom or an ion, I've been writing the number, then the sign. Now, it seems a little pedantic, right? Because really oxidation numbers are kind of like the same thing as the charge. We're not supposed to say that, but it kind of is. And so chemists, I remember we were interviewing somebody, this is a few years ago, we were interviewing somebody and we asked them to actually teach something. Give us a demonstration of your teaching. And they're like, what do I teach? Whatever, anything you want. And so the person said, okay, I'm going to teach about balancing chemical equations. So they went up to the board and they're balancing chemical equations. And they put the sign in the front here which showed oxidation number instead of charge. And like all the chemists were like, you know, like, whoa, right? Like he had major science faux pas, right? And the person was probably brilliant and like they had a PhD and everything, but they got that wrong and everybody's like, whoa, oh my gosh, cringe, right? It's like, you know, on the blackboard. It was just like, whoa, big deal. Okay. All right, so let's try assigning some oxidation numbers. Here is ClO3 minus. ClO3 minus. ClO3 minus. Let's try assigning oxidation numbers to this. Chlorine isn't up here, so, I mean, okay, it's there, but that's chlorine gas. It's a pure element. This is not a pure element. So oxygen, what's oxygen? -2. Okay, so I'm just going to put a -2 there, okay? So -2, and there's 3 of them, so that adds up to a -6. And the overall charge here has to be equal to a -1, because we have that. Okay. So that means the oxidation number on the chlorine has to be +5. Okay. +5. Okay. And this is where people go, wait a minute, you're saying, if I understand correctly, you're saying chlorine has a charge of +5? Everywhere, everything that I've seen up to this point, it's always a -1, right? Charge is different than oxidation numbers. They're not the same thing. Sort of. Okay? It's like you want to go back to your high school chemistry teacher and go, like, what the heck? Okay, all right. All right. So then, where does this all come in? Why do we do this? What's the point of all of this? So, electron transfer is the basic idea behind how batteries work. Now, old batteries might use something like copper and zinc. And there's a great story on this. There's this guy called Galvani. He was an Italian. And what he was doing is he was dissecting frogs. And he had a zinc and a copper scalpel. And he was dissecting this frog, and the copper and the zinc created what we call a dielectric charge or difference. In other words, what ended up happening is it caused electrons to transfer from one to the other. Caused an oxidation reduction reaction. There was no oxygen involved. It was copper and zinc. And when he did this, it caused the dead frog to twitch. Kind of had a little jolt to it. And so he wrote about this. And it was called galvanism. And galvanism was this idea that you could use electricity to cause dead things to twitch. And you're like, huh. Now, fast forward a few years. There were these 2 couples that were hiking in the mountains of Switzerland. I think it was Switzerland. And then this storm starts rolling in. And they decided to take shelter from the storm. So they went to this building up in the mountains. And apparently this is fairly common up in the mountains. They have these shelters because big storms come in and people don't want to die. So they build these shelters. So they go to the shelter, they throw some wood in the fire, and then they just kind of hang out there. And to kill the time, they start telling each other stories. Say, okay, let's just make up some stories. All right. So one of them was Mary Shelley. The other one was Bram Stoker. Mary Shelley tells a story about galvanism and how somebody would take this dead body, take pieces, put them together, and then using galvanism would animate this dead body. Tells this little story. Do you know what this story is? It's Frankenstein. This is where we get the story Frankenstein from. And Bram Stoker says, oh yeah, well, hold my beer. I've got a story for you. And tells a story about the dead rising and the dead doing all kinds of things to the living people. Bram Stoker is the author of, anybody know? Dracula. Yeah. It was because they were stuck waiting out a storm up in the mountains that we get these stories. Like, oh, that is so cool. We need to stick more people up in the, you know, right? We get some better stories out of all of this. So anyway, this is how batteries work, is we're just having electrons transferring from one substance to another. Now, as far as like a test goes, here's a test type question. Here are 4 chemical reactions. Can you identify which ones are oxidation reduction? What you would need to be able to do is write the oxidation numbers on each of these and then look to see where the oxidation numbers change. If the oxidation number changes, then that is an oxidation reduction reaction. So it'd be a test type question.